Chapter 5, Section 1, Reversible Binding of a Protein to a Ligand. Oxygen binding proteins. Oxygen. A few things we need to keep in mind when we're discussing oxygen. Oxygen, if you think back to our chapter on water, like we discussed water and all its properties and things, we discussed the solubility of different things in an aqueous solution. Turns out water was not that soluble. It was poorly soluble. So getting water to be in its gaseous state into a liquid is hard enough. Getting gaseous oxygen, molecular gaseous oxygen, to diffuse through tissues while it's still in that aqueous state has some issues. Because it turns out that, as we see here, it's very difficult for water to diffuse through the tissues because it's busy interacting with all the proteins and lipids and things like that that have all those hydrogens on them. What's holding a lot of those proteins and lipids and things together in stable structures is hydrogen bonds. And you have oxygen floating by, well, it's going to interact. Also, it turns out if there happens to be any metals, any transition metals, iron, copper, things like that, well, they're going to interact with oxygen, slowing down, if not halting, its diffusion. So let's talk about one of these organic compounds that utilizes that interaction of oxygen and O2 and one of those metals. Well, heme. Heme is a great example of the organic compound with a metal at its center that has been harnessed by our cells. You look here, you see these two ring structures. These are porphyrin rings. The one to the left, a protoporphyrin, that's kind of give you a base structure. You see all those nitrogens there in the center. All those nitrogens there in the center are going to be what holds the iron atom that will ultimately interact with oxygen. Here to the right, B, this is the heme that you're going to see in the center of a hemoglobin subunits. Remember, hemoglobin has the 4 subunits, 2 alphas, 2 betas. Each of those subunits is going to have in the center of it B, heme. At the center of the heme, an iron which ultimately, as we're going to see here in this section of the chapter, interacts and stabilizes oxygen as it's distributed throughout the body. It's all based on this porphyrin ring structure you see here. This porphyrin ring structure that stabilizes iron, keeps the iron at the center of a plane. So here's the porphyrin ring. Right there is going to be the iron, and it's in the center of the plane. That whole porphyrin ring is a plane. It leaves above and below, or however you want to orient it, forward, backwards of that ring, open for atomic interactions. What's going to interact with the iron? The iron's being held in place by, its attraction to nitrogen, but there's no true covalent bonds, no true bonds that are holding it firmly in place that would fill in its valence shell. Okay, that's cool, but what's also holding that iron in place? So it's those 4 nitrogens from the porphyrin ring holding it there, holding it, stabilizing it, left, right, up, down. But we also have the forward, back, forward, away, back, away from the plane of the porphyrin ring. Well, it turns out coming in behind the porphyrin ring is a histidine residue. The R group of histidine is oriented in such a way, as we see here in this figure, that the nitrogen from the histidine, R group, can interact with the iron. They refer to this as the proximal histidine. It's going to interact. It's going to stabilize. So, previous slide showed you that porphyrin ring is a plane. In the middle of the plane right there is an iron. So it's stabilized in the plane by 4 nitrogens, leaving here and here open for intermolecular interactions. Well, we now know there's a histidine coming in here that is also interacting, stabilizing it this way, which leaves all of this, as we see here in this figure, open for O2 to interact with iron. Now, it can't just be any iron, because it turns out that the state of iron, Fe2 versus Fe3, also will impact how that iron interacts with oxygen. Fe2 binds oxygen reversibly. Reversibly means it interacts, but then it can release if something else has a greater pull on the oxygen. Fe3, reduced Fe2, has no interaction with oxygen. Okay, so we need to keep iron in an Fe2 conformation. Well, it turns out that, as we're going to see in this chapter, and as you see here in this figure, it's not that one proximal histidine that's going to be interacting with the iron in the middle of that porphyrin ring. There's going to be other R groups in the vicinity that are going to aid in maintaining the Fe2 state of that iron. As we see here, the heme is going to be associated most often with what we refer to as the globins family. It's a protein family. Protein family that is composed primarily of alpha helices, as you see here, and the loops connecting those alpha helices. Secondary structure is primarily alpha helices and loops. Tertiary structure is this folded globin structure you see here. Now, not all the globins, hemoglobin, myoglobin, all of those are going to have the same exact, but it's pretty close to this shape. You'll also notice when you look here at this figure from the textbook that each of the alpha helices has a different designation, A, B, C, D, E, F, G, H. Well, that is an intentional designation, so that as we're discussing the globins family of proteins, and we're discussing differences between the different globins, myoglobin, hemoglobin, and whatnot, that, as we're discussing differences, instead of saying this alpha helice or that alpha helice, which is too vague, we can say differences seen in the F alpha helice. We know exactly where the F is, as you see here. Turns out F, I also pointed that one out because that's also the one that has the proximal histidine that's going to stabilize the iron in the middle of that porphyrin ring. So as I mentioned, there are 4 types of globins that we find primarily in mammals: myoglobin, hemoglobin, neuroglobin, cytoglobin. Different places throughout the body, throughout cells, and throughout tissues, each facilitating the diffusion of oxygen, maintaining a level of oxygen in the tissues for later use by that cell. So we're going to use myoglobin as a great example. It's a simplistic protein compared to hemoglobin, has the 4 subunits. Myoglobin is a single subunit. That's why we're going to talk about it. As you see here, same structure we saw from previous. You'll also notice that on the F alpha helice, you'll see it labeled, that histidine, the one that I've told you about, that proximal one, is labeled as His 93, or it's also known as His F8. Histidine 93 means that if you start at the amino terminal end and you go through the carboxyl terminal end, that the 93rd histidine you come across is right there. That's the one. The F8 means that if you're looking just at the F-alpha helice, that the 8th histidine is that one. So it's two names for the same histidine. It's just, are you looking at the complete polypeptide, or are you looking at just a single motif? And as in all things, especially here in chemistry, we have maths. Maths to help us discuss how things are interacting. So instead of a qualitative high affinity, low affinity, and things like that, let's put some numbers. Let's make it quantifiable, because numbers leave very little room for inferences, interpretation. So we start with, as you see here, an equilibrium expression. P plus L results in PL. Protein ligand gives you protein ligand. The interaction, they are bound or are reversibly bound to each other. Well, how tightly are they bound to each other? I mean, yes, it is reversible, so it's not a covalent bond, but what's that affinity for each other? Is it a high affinity? Is it a low affinity? Is this something that's easy to make, that's really easy to break? Well, we have an association constant, Ka. Okay? Ka is a relative number. Higher the Ka is, the higher the affinity, the more the protein and the ligand are drawn to each other. The lower it is, the less interactions you're going to have between the protein and ligand. So, as in all, we set up the association constant as the concentration of PL over the concentration of P times the concentration of L. Simplified Ka, Kd. So Ka, Kd. Since this is a relative thing, when the ligand is so much higher, that concentration of ligand of L is so much higher than the concentration of P, we really don't see much of a change in PL, or we don't see much of a change in the affinity for things. It's when the concentrations have shifted, there's not much ligand, that we really get to see just how much that affinity is. So you're just, if L's so high that there's always constantly an L interacting with the protein, the affinity of it is swamped. So even if it's a low affinity, there's always going to be some L interacting with the binding site of P. But it's when L is either equal or lower, well, now it starts to make a difference. Well, a little bit of L comes and it just goes away. A little bit of L comes and just goes away. So we need to keep an eye on that. So let's take this a step further. So we want to know affinity, but we want to know how this binding affects things. Does this binding change with changes in ligand? So, as you see here, instead of Ka, we're now going to refer to this as Y. Y equals how many binding sites are occupied, what we think of as the concentration of PL, divided by the total number of binding sites. You'll notice the denominator, PL, concentration of PL, plus the concentration of P. Concentration of P is total binding sites. Concentration of PL is how many of those binding sites are bound to ligand. You go through and you do some algebraic wizardry, as you see there in equation 5.5, and you see Y is equal to concentration of L, the ligand, divided by ligand, plus 1 over Ka. Remember, Ka from the previous is the equivalent of the concentration of Pl. So it's a simplified way of saying Pl. But here, we're taking this a step further. Pl from equation 5.4, which is the concentration of protein ligand bound to each other. So we're saying, here's the total concentration of Pl times the total concentration of L times the total concentration of protein. How much of the L and P is bound to each other, and then the totals of all LP in there. L and P there. Well, Y equals concentration of L divided by the concentration of L plus 1 over Ka is the resulting equation for 5.5. Well, turns out that that equation is quite similar to X equals Y divided by Y plus Z, which is the equation for hyperbola. Gosh, I cannot say hyperbola today. So this is not, the binding of P and L is not a linear thing. Turns out it is a hyperbola, that it'll increase and increase, but there's a certain point where it'll start to curve over more, and it'll never approach 1. Y will never equal 1. To be equal to 1 means that all binding sites have bound all ligand. Won't occur. Will not happen. It'll approach 0.99999, but it'll never be 1. Depending upon what the protein is, what the ligand is, that arc could be a nice gentle, or it could be a straight up and approach 1 and then just flatten off, plateau. Another K number to notice, Kd. Kd is when Y equals 0.5. That means half of the binding sites have been bound with ligand. So that Kd is equivalent to whatever that concentration of ligand happens to be. Now, please notice that we have capital Ka, which is the association constant, and as you see here, little Ka, little Kd, and now we are back to big K sub d. Keep in mind, keep track, uppercase, lowercase k's. So this dissociation constant, where, ligand protein come together, ligand release, come together, release, come together to release. The lower the Kd, okay, because remember this is a relative number, the lower the Kd, the higher the affinity, which means ligand's going to bind and it's going to stick for a bit. Remember, it's still reversible, so it's going to be released, but it's going to stick for a bit. Higher Kd, low affinity, binds, release, binds, release, binds, release. Lower Kd, high affinity, binds, stays for a while, then released. Binds, stays for a while, then released. You look here at this table from the textbook, table 5.1. Gives you a relative idea of this dissociation constant. Avid and biotin, which is to the far left of our scale there, has one of the highest affinity interactions we've seen between a protein and a ligand. And as you move across the scale, you begin to see, where other things fall in. Antigen and antibody interactions. Antibody being the protein, antigen being the ligand, which we'll talk about in the next section of this chapter. To the far right there, you see enzyme substrates. And keep in mind, that scale is a logarithmic scale. So, we're like, 10 to the negative 3 to 10 to the negative 7. Antigen, antibody, 10 to the negative 8, 10 to the negative 12. So, that's quite a bit of difference when we talk reversible binding and reversible interaction of enzymes and substrates. All right, so we've talked about dissociation constant of some P and L. Now let's put something in there for L. So we're going to substitute in, as we see here, oxygen, because we're going to talk about myoglobin. How tightly bound is that oxygen to that iron group in the middle of that porphyrin ring? But the thing is, instead of Kd, we're going to put the, as you see here in equation 510, we're going to put in the 0.5 concentration of O2. What's the concentration where half of the heme and myoglobins present in this reaction are bound? But talking about concentration of oxygen is a bit difficult to do because oxygen's in a lot of things there. So we're going to discuss this as the partial pressure. How much oxygen gas pressure has to be there for heme to be bound, for half the iron to be bound, as we see here, Y equals 0.5. Thus the P50 for, oxygen, the partial pressure where half of the binding sites are bound. What does this tell us when we start studying and we see again it's a hyperbola, so it's not going to be linear. It's not all going to be bound. We take that from the in vitro and we want to discuss it as in situ, in the cell. Well, we also have to take into account that iron in the porphyrin ring, the hemoglobin, the heme, is not going to be just interacting with oxygen. Turns out that iron will also interact with carbon monoxide. Now, as you see here, the bond angles between the iron, the X below the ring, which is with a salmon colored thing supposed to be the porphyrin ring. The X below is the histidine bracing from behind the iron, which leaves that open face above ready to interact with something. We see that oxygen is off to an angle, reversible binding. And as we've talked about in previous chapters when it comes to hydrogen bonding and things like that, angles, anything's off to an angle, it is not as strong as interaction as if everything is in line, as we see here with carbon monoxide. Because of that shift in bond angle and other things going on, turns out carbon monoxide binds 20,000 times better than oxygen, which is why carbon monoxide poisoning is so easy and so deadly for people, because it's displacing oxygen and it's hard to get it to release relative to how easily that iron and that heme and the myoglobin and the hemoglobin release oxygen into the tissues, into the cells. But everything about myoglobin and which we're going to see, hemoglobin later in a few slides. Everything you see here is for stabilizing that porphyrin ring. Not only stabilizing the porphyrin ring, as you see it below the ring, His F8, but we have other R groups, His E7, phenylalanine CD1, valine E11. Their R groups are pointing into that area where the oxygen will be and are helping in stabilizing that angled interaction. By also all of them being there in close proximity, it's minimizing the interaction of other molecules that may displace the oxygen. So when we go and we look at hemoglobin, as it's transporting oxygen from the lungs throughout your body, yes, this is going to happen in the erythrocytes, what we commonly refer to as red blood cells. These red blood cells are formed, by hemocytoblasts. These are precursor cells. Cells that have been told you're going down this pathway but haven't completely been told what you're going to grow up to be, what you're going to mature to be. What's interesting is, remember I told you that hyperbola will never truly be 1, Y will never be 1, no matter how high you raise the partial pressure of oxygen. What we see, as you see here, when you go and you get your blood sats done in the hospital or doctor's office and they say, 94, 96, some people can top out 98 depending on who they are, but it's never 100% because it's never going to be perfect. 100% of all the heme and all the hemoglobin, myoglobins, whatever, will be completely associated with a ligand, with oxygen. Hence, 96, 94% saturation. This is arterial. This is the blood leaving the lungs, going to the heart to be sent out to the body. Peripheral, blood returning, it's about 64%. So about 30-ish% of that oxygen is released to the body. And when you look here, the globin family, myoglobin, hemoglobin, they are quite similar in their structures. The difference being, if you look, yes, they are all alpha helices, and if you count through, they're going to be the same number of alpha helices, some longer, some shorter, But you can see when you look closer that the angles of those alpha helices to each other is going to be slightly different between the two globin proteins. And that's okay. Figure out A, B on the left there, the highlighted areas of blue, low sequence similarity. These are the areas where whatever amino acid's there, as long as it has the correct phi-psi angles between the amino acids to give us an alpha helices, doesn't matter what's there. But when you look at C here, C, and it's a little hard to see, but there are certain amino acids, certain structures, especially in the around the heme, that have to be the same to maintain the shape, to maintain the structural integrity, and to maintain the operational integrity of the hemoglobin or the myoglobin or whatever. The quaternary structure of hemoglobin. We're going beyond myoglobin, which, remember, only had the 1 polypeptide. We're moving up to something that has the 4 polypeptides now. These are all held together. The 2 alphas, the 2 betas are held together by hydrophobic effects, hydrogen bondings, some salt bridges. The alpha 1, beta 1, alpha 2, beta 2, their interactions are held together by about 30 amino acids are interacting. So that's a pretty good. Remember, these are all weak bonds, but remember, they're cumulative. Between alpha 1 and beta 2, so we're now crossing over, there's a fewer, but still enough that cumulatively, all told within the 4 subunits of hemoglobin, you're looking at about 50 plus amino acids that are hydrogen bonding, ionic bonds, hydrophobic effect with each other to maintain that quaternary structure. That quaternary structure is not set in stone, though. Again, conformational changes leading to that induced fit once the substrate or the ligand, however you want to refer to it, tomato, tomato, once the ligand interacts. As we see here, though, when it comes to hemoglobin, this conformational change is between 2 states. First state we refer to R, second state we refer to as T. The R state has a higher affinity for hemoglobin. The R state, the hemoglobin, has a higher affinity for oxygen. I just said that backwards. The T state has a lower affinity. This is what they also refer to as deoxyhemoglobin. The oxygen's not there, so it's not, so it's going to change its shape, twist around. If you look closely to the figures here, you'll see it's a slight twist in the conformation in the presence of oxygen. Increased affinity for oxygen, conformational change means it's going to hold on to the oxygen long enough so it can leave the red blood cells that have the hemoglobin that has the oxygen, can leave the lungs and at least make it elsewhere in the body before that oxygen is given up due to something else having a greater affinity for it. Thus, the hemoglobin will then relax to the T state. The T state, you'll notice here, there's quite a bit of amino acids interaction stabilizing this. They stabilize it and they hold everything together. And this conformational change in the presence of oxygen going from T to the R state, the individual subunits start to twist, start to change shape in the interaction of oxygen. And, you change the tertiary, which is what the individual subunits are. Change the tertiary, you change the quaternary. And it's not massive changes. You look here, T and R. Yes, there are differences, especially if you look at the highlighted blues. Okay, just focus on the blues because they're colored and you can see them better than the gray ones. Remember, each of those tube-like things is, denoting an alpha helice. And you go and you can see the alpha helices twist a bit, they bend a bit in the presence of oxygen as they transition from T to the R state. And it's not just the tertiary structure of the polypeptide. You go and you look at the individual subunits, the alpha, the beta subunits, and you'll see that the heme ring, the porphyrin ring, also changes its conformational state due to the presence, the interaction with O2, which allows for, as you see here in the R state, more of the porphyrin ring to interact with more of the R groups, valence FG5, leucine FG3, leucine F4, to interact and to stabilize. So it's kind of like the porphyrin ring is like this, and when it's with oxygen, it bends back a bit, interacts, stabilizes. And what we see is that as more of the hemoglobin, the subunits of the hemoglobin, bind oxygen, and those subunits, the alpha beta, start to go through their transitional stage, transformation, conformational state, it increases the affinity for oxygen for the other subunits. so that the other subunits will have a greater affinity and will pull in oxygen and will go through the conformational state change themselves, and you see the overall 4-subunit protein go from a T to an R state. We refer to these as allosteric proteins because the binding of one ligand at one site influences the binding at other sites within the protein. Now remember, hemoglobin, even though it, we say hemoglobin, the one protein, it has 4 subunits. Each subunit has its own heme ring, porphyrin ring, which means each subunit can bind oxygen independent of the other subunits. Now, how this interaction, this allosteric interaction occurs, modulating, homotropic, heterotropic, these are just ways to describe the interaction of the subunits or the binding sites with the other portions of the protein. Do they aid? Do they counter? Or is it indifferent? When we look at carbon monoxide, because remember, it's there, we see that carbon monoxide is going to affect the binding of oxygen. Because remember, carbon monoxide has a greater affinity. So when you look here, I'm not going to go over these two. So that's going to affect the conformational change from T to R. It's going to affect, the saturation. Instead of 96, now it's down 94, 90, 80, so on. So the different subunits, oxygen interacting, carbon dioxide, things like that we have to take into account. But that equation we had before, P plus L, PL, our Ka, equilibrium constant, and our Y. Well, that was all based on one protein, one binding site, one ligand type. What if we had more than one binding, one ligand? Now we do. Now we have a means of looking at that. P plus NL yielding PLN. N is the number of binding sites present. Go through, do the same algebraic manipulation of the equations. Ka, PL, concentration of PLN bound, divided by concentration of P, divided by the concentration of L, to the nth power. Remember, N is how many binding sites are present. Go through, do the manipulation for Y. Y, L, concentration of L to the nth, divided by L to the concentration of L to the nth plus the dissociation constant. Okay, we've seen this before. Further manipulation of this, going through and breaking it down, we get, and I'm not going to go through equation 514, 515, I want to focus on 516, what is known as the Hill equation. The log of y divided by 1 minus y equals n, remember, number of binding sites, n times the log of L, the concentration of L, minus the log of the dissociation constant. Wow, it's a lot. What can you do with that? Well, it turns out you can plot this out. Okay? Plot of the log y, the concentration of y, divided by 1 minus y versus the log of L. Y-axis, L-axis. Yes, I know y-axis, y divided by different y's. It'll give us a plot. All your points, best fit line, and then you look at the slope. The slope of the hill plot. If n, the slope is 1, there's no cooperativity. No cooperativity. Greater than 1 means a positive slope. Yes. The different subunits, the different parts are cooperating with each other. Remember the different parts, the different binding sites. Negative slope means there's negative cooperativity. They're actually working against each other. So, go through, substitute in. Instead of L's and P's, let's substitute in our, partial pressure of oxygen. P to the n, P50 to the nth power for Kd. Go through, plot those numbers out. You see that myoglobin and hemoglobin both have a positive slope. Turns out hemoglobin has a slightly altered slope because you have to take into account the T and the R states, high affinity, low affinity states. But even in the low affinity state, at a lower on our plot, it is still a positive slope. So that tells us that when it comes to the four subunits are positively cooperating to each other. Now, how does this work? Are they following one of these two models we see here? The MWC model, the concerted model, all subunits in the same conformation. If one of the four subunits of hemoglobin starts to transition from T to the R, all the others will also do that and have a higher affinity? Or is it sequential, one at a time? A goes, then B goes, then A goes, then B goes. Here's what it looks like when you diagram it out. The MCW model, you notice at the top left there, low affinity state, high affinity state, circles, squares. All subunits are circles, low affinity state, until one of the subunits binds the ligand, oxygen. Forces it go, as you see, as it slides to the right there. Transitional change from the T to the R state. Even, that one subunit, as it transitions, all four subunits transition. And as they're transitioning, they have a greater affinity now for any oxygen present. They can continue down through that linear, each subunit gaining the ligand, the oxygen, or they can go back and forth between high affinity, low affinity, but they're all doing it at the same time. Okay? Or the sequential. First subunit binds, goes to high affinity. Second subunit binds, goes to high affinity. Third, fourth, independent of each other. As I've stated, and I've hinted at, the hemoglobin, myoglobin, and whatnot, or primarily hemoglobin, since it is floating in the bloodstream, it's going to be running into other things other than oxygen. We've already talked about the fact that hemoglobin has a higher affinity for carbon dioxide or carbon monoxide, but has a high affinity also for carbon dioxide. One of those waste products from our cellular metabolism. We need to get it out of the cells, get it out of the tissues, get it to the lungs so you can breathe it out. On the flip side of that, we also need to get some of that carbon dioxide evenly dispersed throughout your body. Okay, because remember, one of our buffering systems happens to be bicarbonate in the bloodstream. So, the carbon dioxide is not of equal concentration throughout our body. Different cells, different metabolisms, and different tissues, things like that. So, hemoglobin also moves that around. We end up with what is known as the Bohr Effect. The Bohr Effect examines this interaction of hemoglobin with pH, take into account carbon dioxide concentrations and so on. So as you see here, changes in pH changes the affinity of hemoglobin to not only oxygen but also carbon dioxide. Hemoglobin, the CO2, which will bind, contributes to the Bohr effect by producing hydrogen, change in pH. Delivery by CO2, CO2 delivered by hemoglobin, CO2 present, Bohr effect means that you can now raise and lower pH, raise and lower, alter the affinity for hemoglobin to oxygen. And there are other regulatory mechanisms for this. Besides the Bohr effect, we also have, as we see here, 2-bisphosphoglycerate. It binds to the hemoglobin protein, and in its binding, they say it affects the affinity for hemoglobin. In my mind, that means it affects the transition of the T to the R state. Because remember, T, low affinity, R, high affinity. So maybe it's affecting that. Maybe it's affecting how all those other R groups from the amino acids are interacting with that area where oxygen is going to be held by the heme group. But what we can see is that, bisphosphoglycerate, as it increases at higher altitudes, you look at this figure here, you see that the saturation, the Y, decreases. The Y50, the partial pressure needed to hit the Y50, 0.5, is actually, 4 times greater, 5 times greater as you increase bisphosphoglycerate. Things get much, much more difficult to maintain blood oxygen levels. BPG interacts there in the center of hemoglobin. You look at the figure. BPG in the center, each subunit, the 2 grays, the 2 whites, 2 alphas, 2 betas, has their own heme group. So since it's sitting there in the middle, as it shows, it states there in that second sub-bullet, it stabilizes the T state. It alters the ability to change from the T to the R conformation. We start making hemoglobin. We start having red blood cells and a fetal state. Turns out that the fetuses, the hemoglobin there, is what is referred to as A2 gamma 2. Okay? A2 gamma 2. Slightly different shape, still a globin protein, still hemoglobin-ish. But this has a low affinity for bisphosphoglycerate. Okay, means it has a higher affinity for oxygen. The metabolism of the fetal cells, tissues, organs is quite high. It's going through rounds and rounds and rounds of mitosis and all of that as it's trying to structure itself, trying to develop. Higher metabolism means higher O2 requirement. So this is how fetuses are able to do that. Textbook brings up this idea of hemoglobin and sickle cell disease. Sickle cell disease, hopefully you remember, is a genetic disease that is passed on. A mutation in the hemoglobin gene, one of the genes for those subunits, specifically the beta chain, as you see here in the second subbullet. Glutamine becomes valine, so the 6th position. Yeah, we know exactly what the mutation is. That small change, glutamate to valine, changes a hydrophobic patch. So you get an altered beta subunit. Remember, 2 betas, 2 alphas, 2 betas. This change results in a hemoglobin that has a high affinity for other hemoglobins. In your red blood cells, you have multiple hemoglobin proteins floating around, hundreds, thousands of them, in every single red blood cell. But as we see here, this, artist's rendition of what's going on, turns out that these beta subunits now have a greater affinity for each other than they do oxygen. And instead of being free-floating proteins with 4 subunits, as you have in the normal condition, you have these hemoglobins that now have a higher affinity for each other and start sticking to each other. And as you see here, they start forming long hemoglobin strands. Start long protein crystals almost of hemoglobin. And what this does is it stretches and distorts what should be a nice round shape with a dimple. Red blood cell, those hemoglobin proteins, those crystals, starts to stretch it out and gives what scientists initially thought of as a sickle shape. Remember sickles that farmers use to harvest plants.